Good morning. Welcome to Turfgrass Epistemology. I'm TravisShaddox. Thanks for joining me. If you're here, you're looking to find how you know what you know about turfgrass science. We're learning how to think critically, learning how to read the literature, and find our way through all this information. Good morning, Andrew Burris, Lush, Connecticut, Cubonican, Brady, Rich the Lawn Guy, Louis Carta. It's raining hard in Columbia, South Carolina. Yeah, it's been a bit, I think you guys end up, or over in South Carolina, South Carolina's a little south of Kentucky, but kind of end up being a day behind us in terms of the weather. It tends to go from our west to our east. And so you guys over in West Virginia and Pennsylvania kind of get what we got a day ago. It's drizzling and gray. It's going to be that way most of this week. And, Mitch Bird's up in Dayton, Ohio. Yeah, same thing. Yeah, it's supposed to let up on Sunday, and then all next week it's supposed to be sunny and a little cooler, but yeah, it's going to be wet and sort of gray and drizzly for most of this week, unfortunately. But we'll take it because, middle of summer, who knows? May go, was it last year before last? We didn't get any rain for, I think, 6 or 7 weeks, 8 weeks. So, I'm trying to hide the UK t-shirt. I have all these shirts from my past positions, and they're all good for working outside. I have all the long sleeve sun shirts, and but they have UK on them, so I'm trying to. I guess it's okay to show them. We have an extremely important paper today, and so I'm not going to go over anything except this paper. I don't have any articles, any periodicals, no videos. I'm just going to go over this paper. Because for several reasons. One, it's exceedingly important paper. 2, I'm afraid I'm going to mess it up. And 3, I don't think I can get through it in an hour. So we're going to get to it and just understand this comes from a very good research team, very good paper, very good journal. It's a little bit complicated, but I'm going to show almost all the results in a PowerPoint slides so that I'm hoping that it makes a little more sense to the average person. But anywho, so the other day, we've been going over potassium for this on Monday. We started potassium. We're going to go over potassium today and for the remainder of March. And I told you all I was going to do we needed to create like a scoreboard or something for potassium. So I did that. Let's pull it up. So each day when I go over an article, I'm going to pull up this scoreboard and I'm going to add to it the articles that fit into the category. So the potassium influence on turfgrass, we have a positive column, we have a column where nothing happened, and we have a column where there was a negative response. And let's see if now you can see my little mouse here. So if the article had a positive response in it, I'll include it over here. If it concluded there was no response, I'll put it in this column. And if there's conclusion in there that was a negative response, I'll include that. So some articles like the Fitzpatrick and Gillard paper from 2004 Monday had both a negative response to potassium and no response to potassium. But there wasn't really anything in there that had a positive response to potassium. And by the way, let me define positive response. What I mean by that is a turfgrass response such as quality or color, or even say cold resistance or winter kill resistance, something that we would be interested in gaining from the application of the potassium. So for example, I'm not going to include soil test potassium increases because of course soil test potassium is going to go up when you apply potassium, but I don't care about that. I care about what happens to the turf. So is there a beneficial response in the turf about something that we care about? So that's what I'm going to include in the positive column. And as you see here, there's just one right now because we went over on Monday. But this will get filled up and there will be a lot of articles in this middle column where it says none. Just warning you. Okay. there are clearly cases in the literature where there is a benefit to applying potassium, okay? But it is nowhere near as common as you might think. There was probably, well, no, that's probably, I was going to, there are ample examples of negative responses as well, where following the application of potassium, there was a reduction in yield or a reduction in color or quality or an increase in diseases and things like that. So we're going to go over all that. So hopefully by the end of the month, we'll have however many articles we go over on this list. And I'll do my best to stay, consistent. We'll see what happens. Okay, so let's get into the article because, like I said, it's an important article, and unfortunately, I think I'm going to mess this thing up. I hate to be negative, but it's just like, I don't know. I'm not very confident about going over this article by myself. I'd rather have Scott on here to help me out, but it is what it is. Okay, so the title of the article is Long-Term Effects of Nitrogen and Potassium Fertilization on Perennial Ryegrass Turf, published by Ebden, DaCosta, Spargo, and Dest in 2013 in Crop Science. So for those of you who don't know Dr. Ebden, he's up at the University of Massachusetts, and he's been there for quite a while. Very nice guy, very, well, at least with me, he's been quite magnanimous, very friendly, very helpful, and he does a lot of good work. His work is several levels above my skill level. Okay, just to be honest. He's very, very good at what he does, and I'm nowhere near his level. So that's the reason I'm afraid I'm going to mess this thing up. But it's a very good team and a very good journal, and it's a very good article. So it fits a lot of categories here that I'm interested in pursuing. I am going to show almost all the results in PowerPoint. I'll go over some of them in tables, but you'll see why when I get to it. But let's read through the introduction. This one has quite a long introduction that I'm going to read because, I think it's important. So it's about, again, long-term effects of nitrogen and potassium on perennial ryegrass. Potassium concentrations of turf and forage grasses can be influenced by a number of factors. So potassium concentration of turf can be influenced by a number of factors, including species, cultivar, age of the tissue, soil texture, in-fertilization rate, mowing strategies, and time of season. And he has, 8 or 9 or 10 different citations in here to support each one of those categories or each one of those influences. And that is one reason. Well, there's many reasons. However many articles he's just cited are the reasons why I am not in favor of taking a tissue test and simply having that one number and going off of that one number to recommend applying potassium. Okay? Well, and I mentioned this on Monday. I've mentioned this in the past episodes as well. Tissue concentrations can fluctuate all over the place. So if you had a population, let's say you took samples from a healthy population of turf, an acceptable population of turf grass, whatever that variation is in that population, that would be the range. Let's say 2 standard deviations would be the range of acceptable turfgrass tissue potassium. But that population is going to change from one month to the next month. The concentration in that tissue is going to change, and it's still from an acceptable population. So you can't just say, well, the tissue should be 2% potassium or 1.5% potassium. And if it's less than that, you need to apply potassium because the cultivar, the species, the age, the texture, the fertilization of nitrogen, the strategies, the time of season, all these things influence that tissue concentration of potassium. And the reason I'm really harping on that is because it irks me that there's so many companies out there that will fleece the turfgrass industry by using turfgrass tissue analyses to recommend fertilizer applications. And what happens is, more times than not, is that when you follow those recommendations, you'll end up having perfectly good turfgrass because you're applying nutrients, you're applying nitrogen or potassium or something like this that can be beneficial to turfgrass. And so then you become convinced, oh, well, the tissue test is working because I follow the recommendations and now I see good turfgrass. The reality is that tissue test recommendation and the interpretation of that tissue test could just be sheer luck And it probably is just sheer luck that they might have happened to, recommended a nutrient to be applied when it needed to be applied. But the majority of times you're applying nutrients when there is no need to apply potassium. Okay, you're applying it with nitrogen or iron or something else that shows the turfgrass response, and you become convinced that that turfgrass tissue test is valuable. And I'm telling you, and I'm not even telling you, look at all these publications, from 1977 to Turner and Waddington to Cherney and Cherney in 2005 there's Miller and Destin Gallard, all these big players in the turfgrass, and Snyder and Cesar, Johnson, Petrovic, Ebden, Hoffman, all these, Sartain, all these publications are contributing to the model of turfgrass science, and they're all saying that turfgrass tissue potassium levels fluctuate greatly. And that's the one reason I just don't have a whole lot of confidence in interpreting that. And they're saying you need to apply potassium because your turfgrass tissue potassium levels are whatever, 1.2. You can have great turfgrass growing at 1.2 or 1.3, whatever, and you can have horrible turfgrass growing at 1.2 or 3. Okay, so keep that in mind if you're a superintendent or a sport turf manager and you've been doing tissue tests and you think that this tissue test for potassium is reliable. It may be that you hit it right on the spot in that particular location at that time of year on that cultivar with that nitrogen fertility application rate and all these things that recommendation was valid. But the chances of that are pretty remote. Okay, so that's the reason why I'm harping on it. It just drives me crazy that there's so many people that are spending so much money on these tissue tests for potassium, and there's almost the scientists have very little confidence in it just looking at a test and saying this is what it should be. Well, you need to know more information before you can have any confidence in that. Okay, this paper is going to talk a little bit about luxury consumption of potassium. So I'm going to highlight this here. Luxury consumption of potassium occurs when potassium uptake is in excess of that needed for normal growth and is problematic because leaf tissue potassium and yield are independent and uncorrelated. Under luxury consumption of potassium, identifying critical tissue potassium or soil potassium levels for optimum growth cannot be effectively determined. So what he's saying is whenever the turfgrass is basically, gorged itself with potassium. It's full as much as it can with potassium. Determining what critical levels may or may not be useful or valid is impossible to do because the turfgrass is already so full of potassium. It needs to be conducted when the turfgrass is not full of potassium, basically, is what he's saying. Okay, so and then he says the accumulation of K, not luxury consumption. Okay, he says accumulation of K, however, can be beneficial to turfgrass stress tolerance by increasing solute accumulation inside of cells, which in turn helps to regulate various important metabolic functions, including turgor potential, stomatal regulation, and osmotic adjustment. He cites Carroll's paper 94. Now, this is I'm not going to, Scott Ebden in my book can basically do no wrong. Okay, so he has a pass pretty much on anything. Okay, I'm just saying that. However, in this case, this Carroll 94 paper doesn't really support all of that. It looked at turgor potential in the leaf. And I'll just say that the Carroll 94 paper clearly shows, and I'll go over the Carroll paper, it clearly shows that the application of potassium has an influence on turgor potential, the water potential in the leaf tissue. And it has a greater potential than, say, calcium or magnesium or other solutes in the tissue. And I'll go over that to help explain that. But, I would just say that it's a little bit of a leap there. Now, he cites his other paper later. Dr. Ebden cites his other paper that is much more sound and much stronger paper when it comes to the benefits of luxury consumption of potassium. And I feel comfortable with that one. So regardless. Research of the effects of potassium on turfgrass growth and its relationship to tissue K has been inconsistent due to many factors affecting tissue K. Okay? So I would say that's the case with a lot of things with potassium. The effects of potassium fertilization is inconsistent. If anything, it's consistent showing positive and negative effects, but majority no effects. But it is inconsistent because there's so many things that affect it, primarily nitrogen. Okay? Long-term studies 4 to 5 years or more to better understand the effects of potassium fertilization on soil K, tissue K, and plant growth have not been studied extensively in turfgrass systems. So that's why he's going to be doing this study. In studies involving turfgrass species, most were 2 to 3 year old tests, and few studies have shown any significant effect of potassium on crop yield. Sartain 93 found a positive effect of potassium applications on crop yield in hybrid Bermuda grass, and I've gone over that paper before, but that's not the, I have not gone over that paper. I've gone over another Sartain's paper, but I'll go over the 93 paper. But he did show a positive influence of potassium on crop yield when clippings were removed, but not when clippings were returned. Okay, so in that paper, we'll talk about the value of returning clippings, because when they were removed, you saw a response, but when they returned, they didn't see any response to applying potassium. The same authors reported no response in perennial ryegrass. So they saw a response in Bermuda grass, but not perennial ryegrass. In perennial ryegrass, Webster and Ebden in 2005 and Hoffman in 2010 reported significant increases in clipping yield with potassium fertilizations only when 5 pounds of nitrogen and higher were applied. So there's a very consistent theme with potassium, if there is a consistent theme with potassium, and that is the uptake of potassium, or the benefit of, and the concomitant benefit of potassium in the turfgrass is highly dependent upon the nitrogen. Okay? Applying potassium by itself almost never shows a beneficial response. And when you apply it with nitrogen, there can be a benefit, okay, in some cases. No response in clipping yield to potassium fertilization have been observed in numerous field studies where typical nitrogen rates have been applied to turf. So I'm going to repeat that because it's vaguely important. And this is going to be very consistent in the literature. No response in clipping yields to potassium fertilization have been observed in numerous studies. And he cites all these studies between 1 pound and say 5 pounds of N. If you're applying 1 to 5 pounds of N, the benefit in terms of clipping yield as a result of applying potassium is very limited, if any. And he cites Watchke's paper and Steiner, Cesar, and Johnson and Fitzpatrick. We already talked about the Fitzpatrick paper. Webster and Ebden. I mean, there's all these papers that show this, okay? In such cases, it is assumed that soil K levels are adequate for growth. However, where soil test K levels have been categorized as low, it has been suggested that the soil test potassium interpretations may be too high and need to be readjusted. And as I said just on Monday and maybe even on prior episodes, I don't know of a case where we've ever gone out and conducted a correlation and calibration, soil test correlation calibration, and found that the correlation, the critical level or the calibration, the amount you're going to apply, is the same as what existed from the soil lab. It's almost always lower. I don't know if it's ever been higher. I'm sure someone can pull it up and post it and say, "Hey, you're wrong." I'm sure it exists somewhere. I've just never seen a case where we went out and properly conducted these tests and found that the critical level was greater than what was already existing in the literature from, say, alfalfa or something else. It's almost always lower. And he's saying the soil test values, many have suggested that when they do this, they need to be readjusted. These soil critical levels need to be readjusted downward. And the reason for that is very likely because turf grass has a greater capacity and ability to harvest nutrients from the soil due to its massive roots and the spreading nature of turf grasses. And even bunch type grasses where all the bunch grasses are completely covering the surface, it has a larger area to harvest those nutrients from. And because of that, the critical level in the soil very likely doesn't need to be as high as it would for, say, corn or alfalfa or soybeans or something like that. Okay? At least that's my take on it. Researchers have suggested that the release of non-exchangeable forms of potassium from primary minerals may be partially responsible for meeting the potassium requirements of turfgrass. Therefore, soil test exchangeable potassium may overestimate the true potassium requirements of turf. Okay? So, and I very strongly agree with that. The soil test interpretation is probably too high because it's probably conducted on another plant other than turfgrass. And it's probably too high because the release of potassium, the mineralization of potassium from minerals, primary minerals like potassium feldspars and micas and things like that, is contributing to the potassium pool that in a way that was not detected by the soil test. So the soil test says you have 40 parts per million, malic 3 potassium. And you go, oh, well, I might need to apply some potassium. When in reality, that 40 parts per million is being contributed to by primary minerals, very likely in many cases, and that contribution is not being accounted for. Okay, so having a single number on a soil test for potassium is probably grossly overestimating the amount you actually need, the critical level, in cases where potassium-bearing primary minerals are present or being applied, say, through top dressing sands and things like that. Okay. So there probably is a range. I mean, we can ballpark the range of critical value levels on a soil test for potassium. I mean, it's probably somewhere between 35 and 45, something like that, maybe. But to have a lot of confidence in saying it should be 40 or it should be 30 or less or it should be 50 or greater or whatever the case is problematic because of all the things that can influence potassium, primarily the contribution from minerals and sources that are not detected on a soil test. In addition, the lack of reliable soil test calibrations using turfgrass as the principal crop under variable culture environmental conditions may also be partially responsible for the inconsistent results with potassium. So that's what I just said with different plants. When we do it with turfgrass, it's different. Most of the long-term studies have been conducted used forage grasses, which is again what I just said. Okay, and then he goes through a whole series of literature on the forage grasses. The objective of this study, objectives of this study were to obtain information of a more long-term field experiment in perennial ryegrass and the effects of varying rate levels of N and K fertilization on clipping yield, soil, and tissue K. So we're going to be looking at 5-year study. We're going to be looking at varying levels of N and K, and they're going to be measuring the dependent variables are going to be clipping yields, soil K, and tissue K. All right. Let's get into the materials and methods. The materials and methods are actually quite short, very straight to the point, which I like. The study was conducted at the University of Massachusetts in South Deerfield, Massachusetts. So for all those listeners in that area, this is right up your alley. Perennial ryegrass was established on August 4, 2003 by overseeding into plots fertilized with NK treatments that were initiated in April 2000. So they had an area that was previous turfgrass on it, and there were some problems with, what was it? It was annual bluegrass, and they went out there and they eradicated it, and then they seeded this into it. And anyway, blah, blah, blah. 15 N to K treatment combinations were evaluated, including 5 levels of nitrogen. We have 1 pound, 3 pounds, 5 pounds, 7 pounds, and 9 pounds of nitrogen per year that were applied as urea. Okay. Then potassium was applied at 1, 5, and 9 pounds in all the combinations of nitrogen. And the source was from potassium sulfate. And that's it. Okay, so we have 5 levels of nitrogen, 1, 3, 5, 7, and 9. We have 3 levels of potassium, 1, 5, and 9. The nitrogen source was urea, which is going to become important because I'm going to talk about, I've talked about pH and how the pH might go up slightly initially, but it will go down after that due to nitrification. And you're going to see that in this paper. And the potassium source was potassium sulfate. So, one can argue that any response could have been confounded by the presence of sulfate because sulfate was not balanced out in this study. So it is what it is. The plots were mowed twice per week at 1.5 inches using a reel mower, and it was selected to represent high maintenance lawns and sport turfgrass. All nitrogen to potassium treatments were applied by hand and watered in with whatever that is, a third of an inch of water, something like that. 0.2 inches of water, something around that. In April 2004 and in 2008, 10 soil samples were taken from the upper 4 to 6 inches of non-fertilized border areas to represent the control plots and analyzed for pH and soil test phosphorus and potassium using the Morgan extract. So we're going to talk about Morgan extract in this whole, well, I'm not going to talk about it. Everything that has to do with soil K is from the Morgan extract. Okay. Soil test potassium and phosphorus in 2004 averaged 119 parts per million potassium and 23 parts per million phosphorus. The potassium was interpreted as medium to high. So 120 parts per million was medium to high for potassium, and the phosphorus at 23 was considered high. The pH was 6.3. By the last year of the test in 2008, soil test potassium and phosphorus averaged 95 for potassium, which went down to low, and 23 for phosphorus, which was the same as it started at high. And the pH was 6 at the end. According to the recommendations of the University of Massachusetts Soil Tissue Testing Laboratory, no supplemental phosphorus and potassium are recommended for established turf when soil test phosphorus exceeds 10 and soil test potassium exceeds 132. Okay, so that's what the soil test lab there in Massachusetts has determined is the critical level for phosphorus is 10 and the critical level for potassium is 132 for using the Morgan extract. Okay. Soil test potassium for each nitrogen potassium treatment plot was determined in April of each year. Okay. At the same time, tissue potassium was determined from clippings collected from all treatment plots before fertilization. In addition, each year of the test, clipping yields were collected in late spring. So they're doing soil test and they're doing tissue tests each year in April. April. Rooting was also assessed in the year 2004 and 2005 during the first week of June. So they're going to be looking at roots. I forgot to tell you about roots. Yeah, they're going to be looking at roots. And that is all of the materials and methods. He goes into the statistical analysis here. If you're interested in looking at that, feel free. The statistical analysis, I have an extremely high level of confidence that it was correct. I'll just say that. Now, what I want to do is go to the results and discussion. And I'm going to show most of this in a PowerPoint. Let me just show one thing in the ANOVA real quick before I do that. He states here that the nitrogen rate accounted for approximately 96% of the nitrogen potassium fertilizer effect on clipping yield, followed by soil pH at 93 and leaf tissue K at 61. The reason he's saying that is because up here in the ANOVA, the nitrogen rate, see this NK fertilizer, the source here, and it shows clipping yield was significant and it accounted for, it had 33% of the effect. And then of that effect, the N rate accounted for 96% of the effect of the nitrogen potassium fertilizer. Okay. For soil pH, the nitrogen rate accounted for 93% of the effect on soil pH. All right. And so in tissue K, nitrogen rate accounted for 61% of the effect of tissue K, whereas the actual K rate only accounted for 32% of the effect on tissue K. So in other words, nitrogen is having more of an impact on clipping yields, tissue K, and soil pH than the potassium. The only thing potassium had a greater impact than nitrogen was on the soil K. Okay, so you're having a greater impact on soil K when you apply potassium. But to relate that to what actually gets into the plant or how it affects the clipping yields of the plant, that's not as influential. It actually is the nitrogen that's causing that effect and a greater effect than the potassium is having. Okay, so let me now go to, I'm going to come back to this briefly at the end, but I'm concerned it's just going to be a little bit confusing if I don't show it in the graph form. Yeah, let me show the graphs, and then I will come back to that. Okay, so now we're looking at some PowerPoint slides that have all these are just the results. I just took the data from all those tables and I put them in a graph format, so it might be easier to visualize. And we're looking at perennial ryegrass clipping yield as influenced by nitrogen. So we have, for those listening, we have nitrogen rates on the bottom at 1, 3, 5, 7, and 9 pounds per year, and clipping yields on the y-axis going from 0 to 8 grams of dry matter per square meter per day. And the perennial ryegrass clipping yield is influenced by nitrogen, as you might expect. As the nitrogen goes from 1 to 3 to 5 to 7 to 9, we see an increase in clipping yield. Not rocket science. You apply more nitrogen, you get more clipping yields. All right? Any bar under the same line is statistically different. So 1 is less, 1 pound of nitrogen, the clipping yields from 1 pound of nitrogen is less than the clipping yields from 3 to 5 pounds of nitrogen. Yeah, but 3 to 5 pounds of nitrogen were statistically the same. And then when you go up to 7 and 9 pounds of nitrogen, which are well above BMP ranges, we see greater increase in clipping yields. The one, I don't know what the BMP range in Massachusetts is for perennial ryegrass, but I imagine it's probably in this 1 to 3 to 5 range per year. I don't think 7 and 9 is going to be in the BMP range. So I would assume that 1, 3, and 5 pounds is kind of what is generally recommended. So that's just kind of what you want to look at. Anything above that is what we do in science to see what the ranges are or should be. Okay, so that's what happens with nitrogen and clipping yields. Let's look at what happens with nitrogen on tissue K. So as the nitrogen goes up from 1 to 3 to 5 to 7 to 9 pounds per year, what happens to the tissue K? And the tissue K, we see goes up a little bit when we go from 1 pound of nitrogen per year to 3 pounds of nitrogen per year. Okay, it goes from about, 2.8% to about 3.1% in the tissue. Perennial ryegrass has a very high percentage of potassium compared to other turf grasses, by the way. And then we see the 3, 5, and 7s are statistically the same, and the 5, 7, and 9s are statistically the same. But basically, we see the point of this slide is that we see an increase in tissue potassium as a result of increasing nitrogen application, the amount of nitrogen applied per year. Okay, so tissue K is influenced by the amount of nitrogen applied. Very consistent in the literature. Now let's look at soil K as influenced by nitrogen. So that's what was in the plant as influenced by nitrogen. Now let's look at what happens in the soil as influenced by nitrogen. So if you I don't know if you've ever thought about this or ever wondered, well, if I keep increasing the nitrogen, what's going to happen to the tissue K? Well, we saw it went up. Well, what's going to happen to the soil K? If we pull everything across the K rates and we say, okay, well, what happens at 1, 3, 5, 7, and 9 pounds of nitrogen per year? This actually, the y-axis says tissue K, but it's soil K. Sorry, soil K is influenced by nitrogen. We actually see the opposite effect in the soil. So the more and more nitrogen you apply to perennial ryegrass in Massachusetts, you will see a reduction in, very likely, see a reduction in the soil potassium, or this was Morgan potassium levels. Okay, the plant is harvesting potassium out of the soil. And if you're increasing the clipping yields by applying nitrogen, then you're decreasing, you're harvesting the nitrogen, the potassium and all the other elements out of the soil if you're removing those clippings, right? So even if you return them, there's going to be some loss a little bit. But you see a reduction, very consistent reduction from the, around 180 parts per million Morgan K at 1 pound of N down to about 150-ish, 125-ish, I'll show these numbers, at 9 pounds of nitrogen. So you're reducing it, not only statistically, but biologically. You're reducing the soil potassium by applying more and more nitrogen. Keep in mind, the 7 and 9 is not particularly relevant to us in a practical sense because we wouldn't recommend these rates. But the 1, 3, and 5, you still see a reduction in soil K. Okay, 1, 3, and 5 pounds of nitrogen. Now let's look at what happens with potassium. So now the perennial ryegrass clipping yields as influenced by potassium applications. So now we have 1, 5, and 9 pounds of potassium. We already looked at nitrogen, and we saw the clipping yields went up when we applied nitrogen. What happens when we apply potassium? So with potassium, there's no difference. This NS here stands for no statistical difference. The clipping yields were the same regardless of whether you applied 1 pound of K, 5 pounds of K, or 9 pounds of K. Now let's look at what happens with applied K on perennial ryegrass tissue K as influenced by applied K. So you applied 1 pound of K, 5 pounds of K, or 9 pounds of K. What happens to the potassium in the tissue? And we do see a little bit of an increase from about 3% from using 1 pound of K. When you 5x that to 5 pounds of K, you got about 3.2%. Something like that. I probably should have put these values on here, but they're in the tables. And there was no difference between 5 and 9 pounds of K. And you're going to see this consistent even on warm season grasses, where once you hit a limit, you can apply all the potassium you want, and you're not going to get any more in the tissue. You can, in other words, he 5x'd it and he got about 0.2% increase in the tissue. I mean, the tissue went from 3% to 3.2-ish% potassium. But then when he almost doubled that again from 5 to 9 pounds of K, there was no increase in tissue K. It stayed at 3.2%. Okay. So there's no need to go out with these extremely high rates of potassium. Once you hit the max, that's it. And even this, I would argue, this increase from 1 to 5 pounds, that's going to be up to you. Do you want to pay that much money for your potassium in your tissue to go from 3 to 3.2? You're 5xing the rate. Okay. Now let's look what happens on the soil K as influenced by applied K. So you're applying 1, 5, and 9 pounds of K. The soil K is going to go up, and it goes up consistently. 1's less than 5, and or 5's greater than 1, and 9's greater than 5. You're going to see an increase in soil K. No one's going to really argue that. The amount of soil K as a result of applying more K, more potassium, is going to go up. You're going to see more potassium in the soil. There's no question. You might see a little bit more potassium in the tissue. Perhaps you're not going to see really any increase in clipping yield according to these results. All right. Now let's switch gears a little bit here. That's the effect of nitrogen and potassium on clipping yields, on soil K, and on tissue K. Nitrogen clearly has an effect on nearly all of that. Potassium has an effect a little bit on the tissue K, a lot on the soil K, and very little, if anything, on the clipping yields. Nothing. So potassium's not having near as an effect as nitrogen on potassium. Okay. So I'll make that clear. We're not talking about nitrogen affecting nitrogen. Nitrogen affecting the actual potassium in the soil or the potassium in the tissue. Okay. Nitrogen's having a bigger effect than potassium is. All right. So now let's look at what happens with, I'm hitting the wrong button here. The relationship between soil K, which is Morgan soil K, and perennial ryegrass clippings. So this is, on here we're looking at the nitrogen 1, 3, 5, 7, and 9 pounds per year. And on the y-axis, we're looking at the R squared value. Okay, so for those who might not be familiar with R squared, the R squared value gives us an indication as how well that model accounts for the variation, or how well we can use a model to predict what will happen. And the highest number is 1. So 1 would be an exact correlation. All right. And if that 1 is significant, then we would know that, yes, we can predict what's going to happen when we apply 3 pounds of nitrogen when it comes to soil K. Or we can predict what's going to happen when 1 pound of nitrogen is applied with soil K if the R squared is 1. If the R squared is below, say, 0.6, 0.7, we really start losing confidence in using it as any means to predict what will happen. Okay. So those are statistical. I'll let the statisticians argue over what number is considered, biologically relevant. But certainly anything below 0.5, what that's saying is the model's only accounting for half of the variation. And we have almost no confidence in using that model to predict what will happen. So on this graph, we're looking at R squared, and we're looking at what's going to happen between the soil K and the clipping yield at all these different rates of nitrogen, 1, 3, 5, 7, and 9 pounds of nitrogen. And what we find is the R squared at 1 pound of nitrogen, so the relationship between soil K and clipping yields is 0. So there is no relationship between soil K and perennial ryegrass clipping yields when 1 pound of nitrogen is applied. And at 3 pounds, it's 0.03. At 5 pounds, it's 0.01. So any of the nitrogen rates that we're going to apply generally to turf grasses, 1, 3, and 5 pounds of nitrogen per year to perennial ryegrass, what this is saying is there's no relationship between the Morgan extract of Morgan extractable potassium and clipping yields. You're not going to see, we're unable to predict what will happen. The soil K could be whatever the number is, and the clipping yield could be whatever it is. There's just no way to know. Now, when you get up into 7 and 9 pounds of nitrogen, which again, we don't recommend, well, I don't think they recommend that up there. The relationship is significant. These 3 stars means that the relationship is significant, but still the relationship is only 0.28 at 7 pounds and 0.35 at 9 pounds. Very, very weak relationship. So there's with the 9 pounds, there's 65% of the variation that we cannot account for, meaning there is a relationship with these 3 stars, but we really don't have, we have 35% confidence. That's not really fair to say that, but we have almost no confidence to recommend to you, yes, you should increase your soil K to this level and you will see an increase in clipping yield. Okay. Very little confidence, if anything, even in cases where there is a significant relationship. Even in those cases, there's very little confidence we would have. Now let's go to relationship between soil K and the perennial ryegrass leaf K. So what is in the soil? How will we be able to predict what will be in the leaf? Will we be able to tell you, yes, if your soil K is 50 parts per million, then your leaf K is probably going to be 3% or whatever. Can we do that? 1, 3, 5, and 7 pounds and 9 pounds of nitrogen at each nitrogen rate? And the answer is no, we can't do that. There is a significant relationship at 3, 5, 7, and 9 pounds, but the best R square is at 7 pounds at 0.18. Remember, we're looking for like 0.6 or 0.7 or greater so that we have some confidence and say, okay, there's, it's possible that you could see an increase in leaf K if your soil K is this. Okay, but at 0.18, even if there is a significant relationship, we wouldn't recommend, we wouldn't provide a recommendation. We have very little confidence in providing a recommendation, I should say. Okay, so we're looking at values less than 0.18 between what is in the soil and predicting what is going to be in the leaf in terms of potassium. Now let's look at the relationship between perennial ryegrass leaf K and the clipping yield is influenced by nitrogen rate. So now we're looking at what's in the leaf, the potassium that's in the leaf. Can we predict what's going to happen with the clipping yield, the growth rate, basically? So if you have low potassium, will you have low clipping yields? So do we need to, if we increase your potassium in your tissue, then it'll be, greater clipping yields? Well, no, we can't do that either. So the leaf K and clipping yield, the best case scenario is a 0.2 R squared at 9 pounds of N. Again, these nitrogen rates we would never apply. Okay, we would not apply this. At 1, 3, and 5 pounds of nitrogen, the ranges that we would normally apply nitrogen to perennial ryegrass in Massachusetts, we have 0.02, 0.03, and 0.01. So no relationship, and it's not significant either. So we are unable, with perennial ryegrass in Massachusetts, to predict what the clipping yield will be based upon the leaf potassium levels, the soil potassium levels, and what was the other one? The soil potassium levels. Oh, and the soil K and leaf K. Okay, so the soil potassium levels or the leaf potassium levels, we can't use those to predict what will happen with the clipping yields. Okay. I'm going to skip through that one because it's not that important. Okay, now let's look what happens on rooting depth of perennial ryegrass as influenced by nitrogen. Now I'm going to show a little bit of this in the table format as well. But in the graph format, we're looking at, on the x-axis, the rooting depth between 0 and 4 inches, between 4 and, say, 10 inches, and then between 10 inches and, well, whatever that is, probably 20 inches or something like that. 10 and, yeah. So we're looking at different depths in the soil profile. So what happened between, what was really important for us, I guess, is the 0 to 4 inch depth. And we're looking at the rooting depth that's influenced by 1, 3, 5, 7, or 9 pounds of nitrogen. Okay. So in the 0 to 4 inch depth, we see 1, 3, and 5 pounds of nitrogen, there was a decline here. Probably biologically, this is significant, but statistically, they were the same. The rooting depth of the perennial ryegrass was statistically the same between 1 and 5 pounds of nitrogen per year. I would argue this reduction here is probably significant from 0.32 to 0.28, but whatever, it's fine. When we increase it to 7 and 9 pounds, we see a significant reduction in rooting depth as a result of applying more nitrogen. It goes from, say, 0.34 at 1 pound of nitrogen down to 0.2. You're almost, you're reducing it by a third, the rooting depth by a third, by applying nitrogen beyond the best management practice limit. 7 pounds of nitrogen, 9 pounds of nitrogen. You're really reducing the mass of roots at that 0 to 4 inch depth, which is probably one reason why they generally will recommend 1, 3, or 5 pounds of nitrogen per year. Because they know if you're pushing it and pushing it and pushing it, you're really, pushing the growth, you're causing other issues as well that you might not want in the long run. It might actually result in greater stress to the plant in the long run because you continue to push it. Well, between the 1 and 3 and 5 pounds of nitrogen, there's very limited effect. So it's probably why they stay at those ranges. At the deeper depths, we see a very consistent reduction from, say, 4 to 6, or 4 to 10 inches. We see a very consistent decline in root mass from 1 to 3 pounds, 3 to 5, 5 to 7, 7 to 9 pounds in. So the more and more nitrogen you apply, the deeper depth rooting, you see a consistent reduction. And then at the very, very deep depths, you see a reduction from 1 pound to any of the other nitrogen rates. If you apply any nitrogen greater than 1 pound, you see a reduction in the root mass at the deeper depths. So nitrogen is having an effect on roots, and it's inverse. You don't get more roots by applying more nitrogen. You're getting, on perennial ryegrass, you're resulting in fewer roots. Okay, less root mass by applying more and more in. Now let's look at rooting depth of perennial ryegrass as influenced by potassium. So I don't know, when I was in the industry, I was over in, like in the Wesley Chapel area of Florida, like the northeast of Tampa area. And I was talking to a guy who was a business owner, and he said, I forget what he was using. He was using like a 1:0:3 ratio. He was using a lot of potassium. And I was like, well, why are you using all that potassium? He was applying to St. Augustine grass. So why are you applying all that potassium? He's like, well, potassium's better for rooting. It helps the rooting. I'm like, where did you get that idea from? I don't know where you got that idea from. But that idea floats around a little bit. Like potassium is the stress element, and it helps with rooting, and it helps stress by influencing rooting or something. I don't know where that came around from, but it sure didn't come from this paper. Because the rooting depth of perennial ryegrass as influenced by potassium it wasn't influenced by potassium at any of the depths. Okay. 1, 5, or 9 pounds of potassium per year had no influence on rooting at whatever depth you want to pick. Okay. So you can apply 1 pound a K. I imagine you can probably apply 0 pounds a K or 9 pounds a K, and you're probably going to come up with the same mass of roots at whatever depth you want to pick. Okay. And that's the end of the data. So let me go back to me, and I will go back to the PDF. So that is the summation of the results. And that is nitrogen had an effect on a lot of stuff. Potassium had an effect on 1 or 2 things, primarily soil K, a little bit in tissue K at the very low amounts of potassium. When you go from that to up, a little bit of potassium, you see a little bit of bump up, but not much. Okay, so now let's go back to the PDF, and I'll read through the remainder of the results. And I think we can get out of here. In a reasonable time. Let me go to this. So let me show table 3. And this is where I pulled all the data from. Table 3 and table 5, I think, is where the data came from. But I want to point out real quick before I move forward about the soil pH. I have mentioned that the use of urea, use of any nitrogen source that can be nitrified, will over time result in a reduction in pH due to the nitrification process. And this paper clearly shows that as well. It wasn't the intent of the paper, but it shows that right here. Over on this table, it says soil pH, and we're looking at nitrogen rates going from 1 pound all the way up to 9 pounds. And you see the soil pH going from 6.1 and very consistently declining down to 5.4. So it reduced by 1/2 of a unit in pH over 5 years. So it is a very slow process, but consistent applications, in this case of urea, resulted in a reduction in pH, but primarily at the very high rates of nitrogen. You did see a reduction, and it was a significant reduction from 1 pound to the 3 pound rate, right, which was 6.1 to 5.7. You did see this is a reduction, but the major reductions were at ranges of nitrogen greater than our BMP limits. But within BMP limits, you'll still see a reduction, which is what they found. Took a long time, 5 years, but you still saw a reduction. So the point is if you're applying urea or ammonium sulfate or any of the ammonium sources that can be nitrified, polymer-coated urea, sulfur-coated urea, all these things, it's not just from, say, the ammonium or the sulfur in, say, like sulfur-coated urea, perhaps. I mean, it's not going to have much of an effect, but it's not just from that. It's actually the process of nitrification of the nitrogen itself will result in liberation of hydrogen ions and a reduction in the soil pH. But that's a very slow process. But just know that it's not. I wouldn't use it as a remediation practice and saying, well, I'm going to apply nitrogen. I wouldn't use it like that. But I would just be aware that over time, you're probably not going to increase the pH. You're probably going to either stay the same or reduce the pH as a result of regular nitrogen applications of urea or ammonium. Okay, so now I want to go down to, well, I'm already running out of time here. I'm going to read this yellow part, and I'm probably going to skip ahead to the other yellow parts because it's a little bit cumbersome, and then I don't have a whole lot of time left. Current University of Massachusetts soil potassium test levels range from 66 to 99 are identified as deficient. Hence, 98 or 2 pounds of K is recommended when the soil test values are 66 to 99. Soil potassium levels averaging as low as 82 parts per million at 5 pounds of K. Oh, no, sorry, 5 pounds of N and 1 pound of K was not growth limiting because no significant increase in clipping yield was observed with additional potassium fertilizations. Additionally, the 82 parts per million soil test potassium level is lower than the unfertilized control border areas of 95 parts per million by the last year of the test. So what he's saying is the soil in the test, potassium levels, was lower than the soil outside the test as a result likely of the nitrogen, right? However, at the 7 pounds of nitrogen, is that right? 7 pounds of nitrogen rate, a positive clipping yield response was observed with potassium fertilization up to 5 pounds per year. Remember, I don't know if that's really relevant because you wouldn't apply 7 pounds in, but that's fine. Where soil test potassium levels averaged 92 parts per million at the 1 pound of potassium rate. These results agree with those reported by Petrovic in 2005, who concluded that potassium recommendations need to be based upon N applications. So, and I agree. I mean, when I give a potassium recommendation, and those of you who know me or have counseled with me or have known my past, I think you would agree with this. And that is, I almost always will say, you don't really need to throw out a whole bunch of potassium. Just apply about half the rate of potassium as you would apply the nitrogen with your normal nitrogen application. So let's say you're applying 1 pound of nitrogen. With that application, just apply about a half a pound of K. Any benefit you're going to see from the K is likely going to be maximized at that rate anyway. You're probably not going to see a benefit from potassium. But if you are, you don't need to apply these very, very high rates of potassium as standalone applications. Just apply it with a little bit with your nitrogen applications. And the reason why I've been saying that for years, decades, I guess, is because of stuff like this, where it says they concluded that potassium recommendations need to be based upon nitrogen application rates. Okay. So if you're going to apply 1 pound of N, your potassium application, the amount of potassium is, let's say, half a pound of K. If you're going to apply 3 or 4 pounds of N per year, your potassium applications might not need to be half a pound of K. It needs to be approximately about half the amount of nitrogen. Now, later in this paper, he's going to explain and argue that the results of this paper conflict with past research when it comes to the N-to-K ratios. Okay, and that's fine. That's what he found. It's fine. But nevertheless, whether it's 2-to-1 or 1-to-1 N-to-K, it needs to be considered, the potassium application needs to be considered as in tandem with nitrogen. Oh, you need to apply 1 pound of K. Well, okay, with how much nitrogen? No, nitrogen is irrelevant. No, it is not irrelevant. It's relevant. Okay. When someone says you need to apply from a soil test, you need to apply a 1/4 pound or 1/2 pound of P, that might be independent of nitrogen. But potassium is not. Potassium applications need to be considered with nitrogen, not as standalone applications. And that's one reason why we almost never see a benefit to potassium, full stop, but certainly by itself. Almost never. Okay. It needs to go with nitrogen. And when it goes with nitrogen, you may, very rarely, but you might see a benefit. Any benefit you're going to see is going to come in that situation, that scenario. And I didn't go into all these combinations up here where there's all the N-to-K combinations. And just because I'm out of time, I'm not going to do that. But you're welcome to go in here and see all these combinations. This is clipping yield, and you'll see clipping yield doesn't change as potassium increases at the 1 pound of N rate. But you'll see the clipping yield will change when you get up into these very high N rates that we don't recommend. As potassium levels increase at the high nitrogen rates, you might see a benefit. But we wouldn't recommend these nitrogen application rates anyway. Okay, I'm going to read this only because it's super important. Significant increases in tissue K levels with potassium fertilizations were observed at all N rates except the 1 pound of N per year. Okay, tissue K, suggesting luxury consumption of potassium at nitrogen rates between 3 pounds and 5 pounds of nitrogen per year. So while no growth response was observed at these nitrogen rates, the benefit, so just let's say, okay, he's saying there was no benefit to the potassium at these nitrogen rates in terms of clipping yields. Okay, so while there was none, the benefit due to luxury consumption of potassium should not be dismissed. And the reason I'm reading this is because I generally will dismiss that. Okay, but coming from Dr. Ebden, you got to pay attention. I mean, you got to listen and say, okay, well, what is he saying? Because he's sharp. Okay, so when he says this specifically, the benefit of luxury consumption of K should not be dismissed. Coming from someone who, like myself, who generally will do that, you had to put down your ego a little bit and go, okay, what is he saying? How can I learn from this? What can I gain from this that I'm missing? And I encourage you to do the same. And he explains it here. Okay. For example, Webster and Ebden in 2005 reported a 0.2% increase in tissue K in the absence of growth with potassium fertilization in perennial ryegrass when fertilized with 1 pound of N. Luxury consumption of potassium was sufficient to significantly increase low temperature survival. So that I care about. Now, you've heard me talk about this for a long, long time. Oh, soil test value is this and soil test value is that and luxury consumption of this. I don't care about any of that. Honestly, I don't. What I care about is what does it do to the turf? How does that have a beneficial impact on the turf? And I'm not saying it doesn't have a beneficial impact. Maybe it does. But that's what I care about. Tell me about that. And that's what Dr. Ebden did. He says right here, it says, luxury consumption was sufficient to significantly increase low temperature survival. So in cases where you don't have a risk of low temperature death, luxury consumption of potassium would be less important. Say you're in, Orlando South, really even Gainesville South. I mean, St. Augustine grass can die up there, but depending on the turf grass, depending on the location, if you don't have significant risk of winter kill, then in this particular case where luxury consumption of potassium might reduce that risk, you don't need to worry about it. But in cases where you might have a location, your turf grass is susceptible to winter kill, then there may be a benefit to luxury consumption of potassium. And I'm going to go into winter kill in the next couple of papers. Okay, but he says it very clearly. It's due to the increase in low temperature survival. That's why luxury consumption of K may be beneficial. But like I said, let's be clear. If you don't have that situation, then luxury consumption of potassium wouldn't be beneficial. He's saying it would be in those cases. Similarly, in this current study, 0.2 and 0.26 and 0.25% gain in leaf tissue potassium was observed under luxury consumption at 3 to 5 pounds of nitrogen, respectively, which may be sufficient to provide enhanced stress tolerance. Now, if I had one thing to say about, anything critical about this, is that scientists in general use this phrase stress tolerance in a very vague way. Okay. We went from talking about the luxury consumption of potassium reducing having an effect on low temperature survival, increasing the low temperature survival, to talking about stress tolerance. And my issue with that is the charlatans and grifters in our industry will take this stuff and say, well, potassium's the stress element. I have a stress blend, and you need to apply this potassium to increase your stress. Because we've used that phrase, stress tolerance. Well, what stress tolerance? Heat stress? Moisture stress? Water stress? Traffic stress? Winter kill stress? Disease stress? Insect stress? Nematode stress? What stress? Well, if we're going to use this vague term and say stress, then we can't get upset whenever, these charlatans in our industry start selling all this potassium and calling it the stress element. In this particular case, he's saying that it wasn't stress, it was specifically increase in low temperature survival, which is a form of stress. But you can't, I think we need to refrain from saying stress tolerance. We need to be specific in our language. What type of stress are you referring to? Because otherwise, it's a very open-ended, black box, basically, of stress. You can put anything in there you want. But potassium probably has no effect on many of the other categories of stress. Okay, but it might on low temperature survival. So very good. Okay, I'm going to go down to the next part here because I'm at an hour right now, and I need to finish this up. I'm going to just hit some key points in the language here, the text, and then I'm going to call it quits because otherwise I'll be here for another hour, and I can't do that. Okay, he goes through that. We're still in the results and discussion. And he says, clearly, clipping yield response to soil potassium is nitrogen rate dependent, which we talked about. There are numerous examples in Table 4 where soil test K levels are deficient for growth based upon current University of Massachusetts soil test recommendations, but few significant crop yield responses were observed. Soil test K levels as low as 46 parts per million, which are lower than the unfertilized control plots, was sufficient for optimum clipping yield response. So he's saying right there that the University of Massachusetts soil test recommendations for potassium overestimate the amount of potassium that you actually need for optimum clipping yield on perennial ryegrass, which is excellent. We find this all the time. But we need people to do this work in order to go to these boards and these groups and have them lower the value down, which hopefully will result in you spending less money on needless nutrients. It says, many have suggested the need to reevaluate current soil test potassium recommendations because they may be too high for turfgrass. And I agree, they're almost always too high. And he has many citations here for this. At 3 pounds of nitrogen in year 2004, a decrease in clipping yields from 5.8 to 4.3 was observed at K rates increase as K rates increased from 1 pound to 9 pounds. 1 pound to 9 pounds? Yeah, 1 pound to 9 pounds. And as soil test potassium levels increased from 145 to 243. So let me read that again because I screwed it up. What he's saying is that the clipping yields he actually measured had a negative impact, or the applied potassium had a negative impact in some conditions, in some cases. Okay? At the 3 pound of nitrogen rate, there was a reduction in clipping yields as a result of potassium as it increased from 1 to 9 pounds of K. And as the soil test potassium levels increased from 145 to 243, they say there was a relationship between that increase, there was a reduction in clipping yields. So here, mark this down for 1 in the scoreboard where there was a negative response. So this study actually, we'll get through it. Ebden in 99 also found clipping yield to decrease with increased potassium from 1 pound to 7 pounds. When the lowest nitrogen rates from 1 to 3 pounds, when the lowest nitrogen rates, that's a typo, 1 to 3 pounds of N. No, it's not. I read that wrong. 1 to 3 pounds of N were applied. Others have also reported less shoot growth in response to higher levels of potassium. Monroe and Christians. Okay, so there's 4 papers right here that have showed a reduction in clipping yield as a result of increasing potassium. Okay, right here. So we'll get to those. we'll get to all those papers. So I wish I knew how this started. I wish I knew how the idea came about that applying potassium can only be beneficial. Because for years, back in the 90s, they would use potassium as a filler sometimes because it was so inexpensive. It was actually, to some degree, less expensive than just normal filler, but it had potassium in it, right? So like, well, let's just go ahead and use this since it's so cheap and it has some potassium in it. Because the thought process was there can't be anything negative happen to it. There can't be any, harmful consequence. I don't know where that started. Someone needs to look that up and send me an email. Because in the literature, it's been consistent for decades. But excess potassium clearly can result in harmful effects to the turfgrass. I mean, you'll see at the end of this month, I won't even get to all the papers, but at the end of this month, you'll see how many citations are in that negative column on the scoreboard, where there's many, many papers showing a harmful effect as a result of applying potassium. I really wish I knew that. I don't know how that came about to where, let's just apply potassium. It's not a problem. It can only be beneficial. No, it can be harmful too. I'm going to read this just to do Dr. Ebden some justice here on this luxury consumption because I'm not a real big fan of this luxury consumption concept, but he's done a lot of work on it. He deserves, his work needs to be brought up to, in the light. As stated earlier, Webster and Ebden in 2005 reported a significant increase in low temperature hardiness under luxury consumption in perennial ryegrass with a leaf tissue potassium gain of 0.21%. However, the same author also noted that shoot water content in crowns increased with nitrogen rate from 1 to 9 pounds of nitrogen. Is that right? With tolerance to low temperature stress decreasing with increasing N rates. So, okay, let me finish. As such, the benefit to stress tolerance with luxury consumption of potassium are also nitrogen rate dependent because shoot water content increases with clipping yield and clipping yield increases with nitrogen. So what he's basically saying here is that you can see a benefit from luxury consumption of potassium, but it's still going to be dependent upon the amount of nitrogen you apply. If you're applying these very, very high rates of nitrogen, you will actually see a harmful effect to the turfgrass. Or you could see a harmful effect to the turfgrass, and any additional potassium with the intent of increasing winter hardiness may be balanced out. It may not be there. You may not be able to realize that because you've already put so much nitrogen on there. The turfgrass is already to a point where the added potassium isn't going to provide the same benefit it would at lower nitrogen rates. Wanted to say that real quick. Let me scroll down to the bottom. Okay, the effects on rooting. So he sums this up pretty clearly here. The effects on rooting of potassium and its interaction with nitrogen were statistically unimportant, regardless of soil depth, which is what I showed. Similar to the effects of potassium on clipping yields, the effect of potassium on rooting in this study and as reported elsewhere have been minimal. So you can mark this down in the did not affect column as well. So we had a negative response and we had majority no response. And I'll put this in the positive column too, because under some very specific conditions, they did show a benefit of potassium, but it was generally only at the very high nitrogen rates that we wouldn't recommend anyway. But nevertheless, this will check all the columns. Now, this is the one graph I was going to show on the actual PDF and not how I was going to do it if I can get it on the screen. Okay, so this is the relation, figure 6. I'm looking at a line graph that is the relationship between rooting in the deepest portion of the soil profile and clipping yields in perennial ryegrass turf in response to nitrogen. So on the x-axis, we have two y-axes. We have nitrogen rate on the x-axis going from 1 pound to 9 pounds. And on the left y-axis, we have clipping yields. And on the right y-axis, we have rooting. And you'll see a very, as clear as you can get it, the beneficial effect of clipping of nitrogen on clipping yields and the corresponding or concomitant harmful effect of increasing nitrogen rates on rooting, which is an X. For those listening, it's an X. As the clipping yields go up in response to nitrogen, the rooting mass goes down in response to nitrogen. Okay, so if you're looking to, for some reason, increase your rooting, this, at least to me, it seems, this little part here in the middle where these two lines cross, forming the center of the X, you would want to be at or below that, because anytime you go above that, you're increasing the clipping yield at the expense of roots. Okay, so just from a 10,000 foot level, I would think that you'd want to be, this is the, 5 pounds of N per year? This is a 5 pound, the X occurs, the center of the X occurs at 5 pounds of nitrogen per year. Okay, so if you keep going up and up and up, yes, you're going to get more clipping yields. You're probably going to have color, the quality is probably going to go up to some degree before it starts to decline. But you're going to see probably increased color and so forth. But you're doing that at the expense of the plant in other areas. Okay, so this 5 pound or less is where you still have some benefit to applying nitrogen. Clearly, have a benefit to applying nitrogen. And you're also balancing out the plant in the terms of like the above ground growth and the below ground growth. You're not completely stripping out the below ground growth at the expense of above ground growth. Okay, and the last little part here is opportunities to keep nitrogen rates to their lowest possible level are especially important for optimum water and nutrient acquisition, and for water use efficiency where less nitrogen promotes greater rooting and minimizes clipping yields, and in turn reduces evapotranspiration. So he's making an argument, basically what I just said, is that don't push the nitrogen way, way up high. Or if you're going to do that, like say you have a tournament coming up or you have a football game coming up and you want to do that, you can push it, but it's kind of like a dragster. Up in Gainesville, you go to the Gator Nationals and they have these Top Fuel funny car dragsters at the end of the runs every time. They can only go, what is it, a quarter mile, or maybe they can go a half a mile if they coast. But they have to replace the clutch every time they do it. Some of those clutches actually melt together. It's so hot. But if you want to go really, really fast, if you want to get a Top Fuel funny or a funny car, you're going to go fast in those dragsters. But you're only going to go fast until you strip the engine out and the clutch melts together and you run out of fuel and all those things. And then what are you going to do? Right? So the same thing goes with the plant. You can push it. You can push the nitrogen and push the nitrogen and push the nitrogen. Say you have a tournament and something up. You can push that and get that quality up and get the growth up and maintain what you want to get. But realize you're doing it at the expense of something else. And at some point, it's going to crash. So to keep it in this middle zone or a little bit below this middle zone where you have a greater efficiency of the uptake of water and the uptake of nutrients and the reduction in evapotranspiration, all these things, this generally is the best management that we recommend. Okay, I understand. You got, the Honda Class is coming up and you want those greens rolling 13 or whatever, and you want everything perfect and everything's great. You can do that for a week or two. But just understand after that is when you want to start, backing it down and letting the grass recuperate. And I think superintendents, for the most part, are all very familiar with that. The conclusions. The strong linear relationship in clipping yields, tissue potassium, and soil potassium to nitrogen underscore the importance of nitrogen rate on interpretation of soil and plant response, especially in turfgrass such as perennial ryegrass that are known to be responsive to nitrogen. It was found that tissue potassium and clipping yield response to soil potassium is highly dependent on nitrogen. There was a strong tendency or strong trend of luxury consumption of potassium in perennial ryegrass that was most likely to occur in the later years between nitrogen rates of 1 to 5 pounds of nitrogen. Okay. The conclusions, he didn't, that's what he said in the conclusions. I left a few things out, I think, of the conclusions, but that's fine. So if I can sum this whole thing up, the conclusions are They found that potassium may have a beneficial effect, but it's highly dependent upon the nitrogen that is applied. Nitrogen generally had a greater effect than potassium on almost every area, including soil potassium, depleted soil potassium, whereas adding potassium increased soil potassium. So there's a inverse relationship there. You're applying a lot of nitrogen, you're getting a lot of growth, and you're removing a lot of the potassium from the soil. Whereas if you're applying potassium, you're getting a lot of potassium in the soil. You might get a little bit more potassium in the leaf tissue, but you're not influencing the clipping yields hardly at all. Very, very little. Certainly within the nitrogen recommended ranges of 1 to 5 pounds of nitrogen per year for that area. You're not going to see a major or any real meaningful benefit in terms of clipping yields from applying potassium. Okay. And finally, don't forget the pH of the soil declined over 5 years as a result of applying more and more nitrogen. And the roots declined as a result of applying more and more nitrogen. They did not change as applying more and more potassium. So there really was the benefit of nitrogen in terms of rooting would be at the lower end of the nitrogen application ranges. 1, 2, 3, 4 pounds. Well, 1, 2, 3 pounds. The rooting was about the same. But once you really push it up to those higher nitrogen rates, is when you start to see declines in rooting. Okay, but the potassium had no effect on rooting at any depth, and that's going to be pretty consistent in the literature. However, I already have shown a paper months and months ago. I will show a paper that did find or conclude that the rooting was influenced, and this was on Bermuda grass, rooting was influenced by potassium. But I'll contextualize that so we're aware that was in a very specific case where potassium was extremely deficient, very, very, very low. In this case, it was low according to the existing soil test interpretation for Massachusetts. But they showed that clearly it wasn't low enough. The turfgrass was still fine. Even at the very lowest potassium level, the turfgrass was still growing fine. So their interpretation was too high. But in the warm season grass paper that I'll show you, at least one, maybe two papers, where we do see a response to potassium, both in the leaves or the growth and the roots, those were in cases where the potassium was not just interpreted as deficient, it was deficient. There was not enough potassium in the soil to maintain adequate growth. And I'll get to that. Okay. All right, guys. Anything in the chat for me? Are you guys chatting with yourself maybe? That's fine. So Samuel Asamoah. I like that last name. That's a fun name to say. Asamoah. Is 7 to 9 pounds allowable in sport turf? If not, what are some complications that stem from high amounts of nitrogen apps aside from the shortened roots? Well, I don't know about every sport turf situation. I will say that in Florida, I did my best to partition sport turf as a standalone sort of entity, because in some sport turf situations, you're basically in a constant state of establishment. So normal BMP recommended nitrogen applications will not suffice in many of those cases, because you're not in a normal situation for turfgrass. You're constantly getting it beat up and constantly growing it in, constantly trying to keep the growth rate as high as you can get it, because you need to maintain a safe playing surface. So 7 to 9 pounds, believe it or not, it would not be, to me, outrageous in some situations on sport turf. That would not be, in my opinion, crazy. It depends on the sport. It depends on whether it's high school or pro or municipal sports. I mean, they're all different in terms of their damage to turf. So I can't say every case in 7 to 9 pounds would be allowable. It depends on the location, but it's possible. And then it says, if not, what are some complications that stem from high amounts of nitrogen applied, other than from shortened roots? What are some other harmful effects of over applying nitrogen? I would say primarily it'd be from the shortened roots and the reduction in carbohydrates, because you're stripping everything out of the roots to assimilate that nitrogen. You're stripping all the carbohydrates out of the roots and the stems to assimilate that nitrogen. I would say that's the major deleterious effect. There may be some other diseases and other susceptibility to insects and things like that I'm not privy to, but there may be something there on that. But I would say primarily it's a result of the root reduction would be the primary, and then whatever consequence would occur as a result of that. So reduce water uptake, reduce nutrient uptake, reduce carbohydrates, and all these things. Beep, beep, I'm a Jeep. I don't know how you guys come up with all these names. I like that name too. I got 2 new names, Samuel Asamoah, which is a really fun name to say, and then beep, 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 I'm a Jeep. I drive a Jeep too. I have a Jeep. After finding this channel, I feel that I have to unlearn almost everything that I have learned from YouTube and the internet. Very frustrating, but at the same time, very helpful. Well, thank you, beep, beep, I'm a Jeep. I'm gonna tell my son that name. Beep, beep, I'm a Jeep. That's a fun name to say. You know, it is what it is. I've used this analogy a number of times. I was in martial arts for ages and ages and taught martial arts for ages and ages. And I was in MMA. I was Brazilian Jiu-Jitsu and so forth. And when people come in, whenever the Brazilian Jiu-Jitsu fad came around and say like mid to late 90s, a lot of people started coming in wanting to learn it from other disciplines. And it's not necessarily that their other discipline was wrong, like say Taekwondo or something. It's not like Taekwondo is wrong. They can kick a lot better than I can ever kick. But they want to come in and learn MMA. And then you have to unlearn your muscle memory, and your body is just, it's so used to doing it one way that it's very difficult to recondition their mind and their body from Taekwondo into Jiu-Jitsu. It's not easy. It's much easier to take someone who doesn't know anything about martial arts and let's say they want to learn MMA, take them and train them because they have a fresh mind. They don't have any presuppositions or anything that's restricting them back. So I guess what I'm saying is it's very understandable. Beep, beep, I'm a Jeep. It's very understandable that that's the case because you've learned it one way and now you realize, oh, wait a second, there probably is a better way, and you're having to recondition your mind. That's very common. It's very normal. And, unfortunately, if you're getting your information from YouTube or, many other social media sources, it's probably, I don't have a lot of confidence that it's accurate. If you're getting your information from the universities and from the extension resources they have and so forth, then you probably were in a better path. But, it's all good. I wouldn't lose any too much sleep over it, but you're here now. So we'll try to get through it. Louis Carta says, Dr. Shaddox, do you have any input on nanotechnology specifically to nutrient uptake, in this case, enhancing nitrogen uptake in the grass point? Now, I'm not a nanotechnology specialist at all. I will say that I want to know what your definition of nanotechnology is first. There are a lot of charlatans. I'll just come out and say there are just a lot of people fleecing you guys by selling nanotechnology. I had a guy come in my office one time and said, I have the best nitrogen in the world. It's the smallest nitrogen in the world, and it gets taken up into the leaf more efficiently because it's so small. I'm like, well, you reduce the size of the element nitrogen? I mean, come on. So he didn't understand what he was saying. He was just spewing a bunch of nonsense to me. So this, it depends on what you mean by nanotechnology. There's actual physical particles, let's say nanosilicon, that may have some benefits. I know they have benefits in dentistry. They may have some benefits in the placement of certain chemicals in agriculture. But when it comes to the actual size of the element, nitrogen or phosphorus or potassium or those sizes, that's another definition of nanotechnology. So I would say there is at least potential there. But when it comes to whether or not I'm confident recommending it or using it, that's a totally another thing. I haven't seen any evidence to convince me that I should spend more money on it. That's what I want to drive home. And I'm going to show a video. I don't know if I'm going to be on tonight or tomorrow night, but I'm going to show a video where I have no knowledge of what they're talking about. And I'm assuming, perhaps incorrectly, that you would be in the same boat. I have no clue what they're talking about. But if they're not going to provide me with any convincing evidence, there's no reason for me to buy their product. There's no reason for me to be convinced to spend my hard-earned money on some whim of, oh, well, it sounds good in the marketing. So the same thing goes with nanotechnology. I don't have any knowledge or any strong convictions one way or the other with nanotechnology and turfgrass because I haven't seen any evidence. So until I do, I'm not going to spend any money on it. And I hope that's sort of the direction that we take in general on as we progress through our critical thinking development, is that if there is no evidence provided to convince me, then there is no good reason to use it, regardless of what the product is. Okay. And Ignacio says, am I going to go over PGR, plant growth regulators? Yeah, I will eventually, but I'll be honest, Ignacio, that's about the 8th thing on my list. So it's going to take some time. I mean, the channel's not going anywhere, and I know everybody's anxious, and I love that. I love the fact that you guys are so interactive and send me emails all the time. That's fantastic. I tend to be wired in a certain way where I want to stay with a topic for about a month or so, and I'm not going to go over the whole topic in a month. There's no way, but I go over a topic for about a month, a couple weeks, whatever, and that way people kind of know, hey, Travis is going over this for the month, and you can kind of go back and look and kind of follow that topic, and then I'll go to a different topic. And I feel comfortable with that method, although some people may prefer a different method. I feel comfortable with that because mentally my thought process is focused now on potassium for the next several weeks. And then I'll go to PGRs, or I'll go to phosphorus, or I'll go to soil testing or whatever. But it's going to, it might be a while. But that's generally the way I'm moving. Oh, Samuel Asamoah says, thanks for the response. I was referring specifically to golf. 7 to 9 pounds allowed. Well, I'll say this. That's a more specific question, Samuel. So I'll say this. So the question specifically is 7 to 9 pounds allowed in golf? Every state in the United States now has a golf best management practice manual. And in that manual, and you can go download them all. They're all available for free. I think it's through the GCSAA. You can type in just GCSAA state BMP manual or something along those lines, and you'll see a list of every state's BMP. Okay. In that BMP will be in the manual will be best management practice for nitrogen applications. So whether it's on a tee or a fairway or a rough or a green or a practice area, the nitrogen application rate BMPs are very likely to change, and they're very likely to change from state to state, and even within a state from grass to grass. So that's where I would go if you wanted to know whether or not it's allowed. Because, well, I'll just leave it at that. I'll let the states and the specialists in those states determine their best management practices for their specific site location. Okay? All right, guys. If I'm on tonight, you'll see something pop up on the YouTube channel for a link. And if not, I'm more than likely going to be on. I'm going to move from the Wednesday night to Thursday nights. I'm more than likely going to be on tomorrow night at 9 p.m. Well, one way or the other, I'll either be on tonight or tomorrow night. And I'm going to leave you with some Kenny Rogers. Not country music, but the best song he ever sung as we close. I appreciate everybody. Thanks for coming. I'll see you next time. Bye.